and so you couldn't actually get to this assignment. You should be able to now. So if you could like double check that you can actually get to it, and if not, let me know because I'm a big idiot. Um, okay, so I wanted to point out one other thing here before we get cracking, which is I have a link to this file on Dropbox, which are some notes that I've been writing on floating point, which I, you know, need to update them, I'm sure. Um, but anyway, they've got some more examples and some stuff like that. So there's a link to that there, and yeah. So just FYI. Okay, good. No. All right. So let's get back to it. Minimize this. Back here. All right, so just to recap, right, that what we basically want to do is first take whatever number you want to encode and write it as if it's sort of a binary decimal. Okay, so sort of math class style. And then from that, figure out what would it be in sort of this scientific notation style thing, okay? Uh, and then we can encode it. So the things to remember: the mantissa always is 4 bits, and the leading one you don't have to encode, right? Because we get that for free. Um, and so you, depending on what your number is, you may have to, like, let's say that you write down your number, right? And you're like, wait a minute, I need 7 bits for this mantissa. Well, sorry, you only get 4. Okay. And so what that means is that you can't precisely encode the number that you're after. Okay. Um, okay. And we'll look at an example of when this sort of thing can happen. The other annoying thing is, of course, the exponent looks bigger than it is. Okay. So it's offset by 3 in this case. And in case you're wondering about the formula, um, it's this. Okay, so you take the number of exponent bits, take away 1, do 2 to that number, and then take away 1. Okay, so in our case, how many bits are we using for the exponent? 3. So take away 1 from 3 and you get 2. 2 squared is 4. Take away 1, you get 3. And that is the offset, the bias. Okay. Um, for 32-bit, we use 8 bits for the exponent. Excuse me. So if we use 8 bits for the exponent, what would the bias be according to this? Well, what's the formula for it? Two to the right, 2 to the 8 minus 1, okay, or 2 to the 7 minus 1. What's 2 to the 7? Huh? 2 to the 7th? No, that's 7 to the 2. You need some more coffee. And where's Cody? All right, let's pull out the Snapchat. Pull out the Snapchat. Maybe he's still mad at me for making the very obvious low hanging fruit of a yo mama joke last time. Okay, well, good. Uh, you know, you do what you can to keep your students engaged till 8 o'clock in the morning. So, all right, so it's 127, right? So 2 to the 7th is 128. Take away 127. Okay, great. And that, by the way, holds for all of the IEEE compliant standards. So it works the same way every time. It's just figure out how many bits you've got. Okay, so those are the two kind of annoying things. So let me actually go back for a moment to our good old friend Float Toy. Can find it here amongst the pun intended sea of floaty toys. You see what I did there? Yeah, okay. Okay, so one of the things I like about what the page defaults to is notice that all of the numbers here are approximations of pi, right? So this is like I said, a useful number. And you'll notice that the precision at which you can encode um, pi depends on how many bits you're using, okay? And that kind of makes sense because if I said you're allowed to use 4 decimal digits or 8 decimal digits, well, clearly you could approximate pi more precisely if you had 8 decimal digits than if you had 4, right? Duh. So we should expect the same kind of thing to be the case if you're doing this in binary. And so, okay, here's what the approximations come out to in using 16, 32, or 64 bits. And what we'll do now is figure out, okay, well, what would be this sort of horrible 8-bit encoding for pi, and how good can we get it? Okay, does that make sense? Okay, so 3.141 is the best we can do with the 16-bit encoding. 3.14 is kind of probably what you guys all memorized in school, right? That's usually good enough for most purposes. I mean, unless you're sending space probes to Mars. Anyway, so let's figure that out. Okay, so so the first step we need to do is write down the number as best we can as a sort of binary decimal looking thing. Okay, so pi, of course, so let's just write it down and as a base 10 number, and then we'll start to encode it. Okay, now the 3 part of it is easy. What's 3? 1, 1, point something. Okay, good. The 0.14159 blah blah blah, we'll have to do a little bit more work here. Okay, and for sake of simplicity, let me bust out a little calculator here. Actually, you know what? I'm going to do one better. I'll just use Python. Okay, so what is the position to the immediate right of the radix? What's its place value? Okay, the tenth's in base 10, but in binary, what is it? The halves place. Okay, can a half fit into 0.14159 blah, blah, blah? No. So that place has to be a 0. Okay, what's the next place value? Quarter. Can a quarter fit into 0.141 blah, blah, blah? No. Okay, what's the next place value? An eighth, which is, as a decimal, what is that? 0.125. Does that fit into 0.141 blah, blah, blah? Yeah. Okay, once with a little bit left over. Okay, And so let's talk about the little bit left over bit. Okay, so what I need to do is I need to take 0.141596, basically whatever, and I need to subtract the 0.125, and this is my leftovers. Okay, and then what would the next place value be? The 16th place. What is 16th, 116 as a decimal? Yeah, 0.0625. Okay. Does 0.0625 fit into 0.016 blah, blah, blah? No. So the next place here would be a 0. Okay. And then we would continue this process for as long as we wish, right? With pi, of course, we'll never finish. Um, but I'm going to stop here for the sake of our demonstration. And why am I going to go ahead and stop here? Because we already have enough bits worth of stuff, right? How many bits do we get for our Mantissa? Well, it depends on how you want to count. It's either 4 or 5, right? Why 5? Because what's true about the first number that you, like if I write something down, I'm going to write down 1.x time or 1 point Mantissa times 2 to the exponent, right? Do I have to actually encode that leading 1? No, because it's always a 1, right? So I get a bit for free here. So even though the Mantissa, we only store 4 bits, it's really more like 5. Okay, so my Mantissa here would be these 4 bits, okay? The stuff to the right of the immediately, the first one, okay? And 4 bits worth. So did we need to deduce that far right bit was a 0? Not in this case, because we wouldn't have had the bits to represent it anyway. Okay, but the reason I mention that is how to continue this process is if we continued the process, that's how we would get the mantissas that you see here. Okay, there's just more bits to work with. Okay, so what's our mantissa? 1001. Okay, what's our exponent? Well, first off, okay, I need to write this as 1 point something. Okay, and if I move the radix to the left 1 place, then I have to compensate by multiplying by 2. Okay, remember when I told you guys my tales of woe of being a Kohl's employee? Okay, um, moving the radix in binary is basically the same as either multiplying or dividing by 2. Okay, and so if I move the radix to the left, that's like dividing by 2. And if I then multiply by 2, well, those cancel each other out, and I basically have the same thing back, right? Okay, so, and remember, right, what's the convention for sort of scientific style notation? How many things go right before the radix? Precisely 1 digit, okay? And in our case, that has to be a 1, because what's the only other digit it could be? A 0, and we said that that's bad. Okay. 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 So are we cool that this is our number in sort of the scientific style notation? Okay. And then we got to figure out the exponent. So the exponent, when I wrote it in scientific style notation, is 1. Okay. And what am I going to actually encode, though? 3 bigger than that. Okay. Because remember, we've got that annoying offset. Okay. So the exponent I want to encode is 4, okay, and that I will encode here as 100. Okay, is that okay? You guys don't seem to be buying it. Okay, well, so how would I really think about this? What is 1? That's 1, right? Okay, because what's 3, of course? 1, 1, right? And then do the addition, and this is what you get. Okay, is that okay? All right, so the final encoding is going to be what? What goes very first? Huh? I'm sorry, I can't hear you. What goes first? Which bit? The sign bit? Yeah? What's the sign bit here? You got 2 choices. Why is it a 0? It's a positive number. Okay. Okay, what comes next? Which bits come next? The exponent bits. What are the exponent bits? 1, 0, 0. Okay. And then lastly, the Mantissa bits. What are the Mantissa bits? 1, 0, 0, 1. Okay, so let me color code this. Or actually, I'll color code it. All right, so what was the color scheme we used? Blue for exponent. Oops, that's not what I wanted. I wanted background. Blue for exponent. Green for, or sorry, blue for sign bit. Green for exponent. And red for Mantissa. Okay, so are we good with that? Yeah? Okay, so let's actually compare this to, well, there's 2 questions we want to answer. What actually is this as a number, right? So if I were to go back and decode this back to base 10, what do we have here? Do we have 3.14? Do we have 3.141? What do we get out of this? Well, it's actually, we can answer that by going back up here, right? Because what would this number be? This would be 1 point, a half, no quarters, no eighths. What's 1/16? Well, actually, let me write it like this. And, okay, so this part here, right, is 1 plus, there's a half, there's no quarters, there's no eighths, there's a 16th, okay? But then what do I have to do to this? Multiplied by 2, right? Okay, so then what do I really have? I have 2 plus 1 plus no halves, no quarters, and an eighth. And so what I get is 3.125. That's the closest we can get to pi with 8 bits. Oui ou non? Seeing some confused looks. So questions, preguntas, fragens. Yes. Okay. Why is the bias 3 or why is there a bias at all? Which one's your question? Okay. The bias is 3 because so the formula for it, right? How many bits do we use for our exponent in this case? 3, okay? Take 1 away from that. What's 2 to that number? Now take away 1, and you get 3, okay? So it's coincidence in this case that the bias is the same as the number of bits, okay? But in, like, say, the 32-bit scheme where you use 8 bits for the exponent, the bias is 127, okay? And how do I get 127? Well, if I have 8 bits for an exponent, take 1 away, that's 7. What's 2 to the 7th? Well, calculate, 128. Take 1 away from that, you get 127, okay? Um, yeah, so that's how you figure out what the bias is, right? Is just based on the number of bits in that little formula. Yes, okay. So good point. So this bias of 3, every time we encode a number in 8 bits, there's this bias of 3. And it's constant within the 8-bit system, okay? If we say, okay, throw it out and let's do 32-bit encodings, now that constant is 127. So once you pick a number of, which number of bits you're using for your encoding scheme, then the bias is fixed, okay? Now, one of the benefits, by the way, of that formula, and we'll look at this in a second, so right down here, look at what your sign bit, your exponent, and your mantissa are. Okay, and let's compare that to what it is on the 16, 32, and 64-bit standards. Okay, so this is why this pattern is actually kind of nice. Well, first off, our sign bit's 0 for all of them, right? That's obvious. Okay, but look at the mantissa here. What was our mantissa? 1001. Well, look at the start of the 16-bit version. It's the same thing, but they have more bits, and that gets them more precision. Okay, ours stopped here. Okay, also, what was our exponent? They have more bits, but otherwise it looked similar. Okay, and if we keep going down, this pattern continues, right? What is the mantissa here? It starts the same as our mantissa, plus a whole bunch of extra stuff. Okay, great. And even on the 64-bit, this is true, right? So there's a nice pattern to this. And maybe that's one reason why this bias, as annoying as it is, it being cleverly chosen, means that this isn't as horrible as you think, right? So if you've got, so what's nice about this standard then is we could have answered our question of how to encode pi. If you know how to encode it in 16-bit, you then therefore know how to encode it in 8-bit. Okay, so what bits from this 16-bit version would I take for my 8-bit? Well, the sign bit's obvious, and then I take the most significant bits from each thing, right? So 100, exponent, 1001, mantissa. Okay? That doesn't work perfectly, but in every instance, but right, we kind of get the idea. Okay, yeah. So 3.125 is the best that we can get pi with 8 bits, and I think you guys would agree that that's pretty crappy. Okay, in terms of an approximation. And so this is why this 8-bit system, nobody in their right mind would ever actually use it. Okay, it's too imprecise. Uh, if we compare that, though, to, well, 3.141, yeah, I guess that's good enough if you're in elementary school, right? But to really do anything with any degree, reasonable degree of precision, you got to step up to 32 or 64 bits. Okay. Yeah. Now, I guess this gives me a moment to digress. Does anybody know what the almost became official Indiana approximation of pi was? 3. So a little over 100 years ago, and I'm not making this up. So basically, one of the things that we mathematicians have to deal with on occasion are what we call cranks. These are people that think they know mathematics and they maybe know quite a bit of it, okay, but they don't know it well enough or they're crazy enough to think that they've proven things or discovered amazing results that are basically bullshit. And so there was this dude that um, basically claimed to have discovered all kinds of miraculous things. And he basically got the somebody to sponsor in the General Assembly a bill that so would name him as the discoverer of all these amazing truths. In exchange for that, he would allow his magical discoveries to be used in Indiana public schools without royalties. And one of the consequences of his garbage is that pi is 3. Now, fortunately, Professor Waldo from Purdue happened to be at the State Assembly building when they were voting on this and saved the day, and pi was not re-legislated to be 3 in the state of Indiana. So we lucked out on that one. But I mean, this is Indiana, guys. Like, I mean, this is the crap you expect out of like Arkansas or Mississippi, right? Not Indiana. So, yeah. Anyway, okay. So, yeah. So the 8-bit system, right? Like, what it's good for is it has a small number of bits and therefore is a little easier to manage. But it also kind of forces us to recognize that no matter what kind of system we use, there's going to be a limitation, right, in precision. You can't be perfect. Them's the breaks. Okay. Okay. So good. All right. So let's maybe flip this a little bit and do a decoding instead of an encoding. And let me just steal one of my encoded numbers. All right. That's what we just did was pi. Don't want to do the special encodings. We'll talk about arithmetic on Friday. All right, so let's just take this one as for sake of example, and let me highlight this stuff appropriately. Okay, so we've got our exponent bit, our Mantissa bits, and our, okay. So let's say that this is our mystery number. Okay, how are we going to decode this? Okay, so this is sort of the reverse process of what we've done so far, right? We need to take this and write it as sort of a binary style scientific notation thing, and then sort out what that is, okay? All right, so what's the low-hanging fruit here? Huh? It's negative, all right? We've got a negative sign bit in this case instead of a positive sign bit. Um, and by the way, if we knew, like, for example, here, that number is pi, Well, then it's real easy to encode negative pi. You just flip the sign bit. That's it. Everything else stays the same. That's kind of nice. It doesn't work that way for integers, as we've seen, but it does with floating point. Okay, so we know that our number is negative. So let's worry about the rest of it. Okay, so if I were to write this as 1 point mantissa times 2 to the exponent, right? And let me turn off this highlighting because this is starting to get annoying. Okay, that's where I need to start. Okay, what are my mantissa bits? Okay, that's easy. We just plop them in. Okay, what is our exponent in this case? What's encoded there? No, it's not 3. It's 4. Okay. All right, so what's encoded for our exponent? Right, what's the number in green there? It's encoded as 4. What does it count as? 1. Okay, how did I go from 4 to 1? I what? What did 3? I added 3. How about subtract? Yeah. Okay, so why did I subtract this time where I added before? Huh? Yeah, exactly. I'm going backwards, right? So when you're encoding, you do one thing. When you're decoding, you do the other. Okay, is that all right? Okay, so my exponent looks like 4, but really is a 1. Okay, and now we just have to figure out what all does this mean. Okay, so times 2 to the first means I need to move my radix how many positions and which direction? 1 to the right. Okay, so now my number is this. Okay, and so now we just have to go through and do the place value. All right, so what do I have in the, what's this far left position here? This guy, which place is he in? Huh? No, it's to the left of the radix. So the stuff to the left of the radix is the whole numbers, right? So which place is he in? The twos place. Okay, so we've got a 2. We have no 1s. What's this 0 that I've highlighted there? What position is he in? The halves place. So do we have any halves? Nope. What's the next bit? 1, which is in the quarters place. And then our last bit 0, so we can stop. So our number is negative 2 1/4. Okay, does that make sense? Yeah? We? You'll notice, by the way, these floating point notes, did you see when I last updated them? It's like February of 2020. You know, because a funny thing happened in March 2020. The world went to hell. So, I mean, you guys remember, right? I remember. Yeah, remember berries, South Park. It's pathetic. Okay, so we get negative 2 1/4. Okay. All right, so questions on the decoding side. Okay, it's a similar process, right? You're just basically doing everything in reverse. We? No? Okay, so let's sort of talk about the, there's an issue of precision, okay? And one of the things that's a little funny about this So let's kind of think about it. If we've got 8 bits, and we say that we're going to use 1 for sign, let's just for the moment ignore all the negative numbers, okay? Then we have 7 bits left over, okay? And how many things can you encode with 7 bits? How many total things? 2 to the 7, which is 128. Okay. And that makes sense, right? With 8 bits, you can encode 256 things, right? We're sort of thinking about just the positives for the moment, so we'll leave the sign bit off. Okay. So I can encode 128 things, okay? Now, let's figure out what's the biggest positive number that we can encode with this system, okay? What's the smallest positive number that we can encode with this system? Well, maybe you could say 0, right? But there'd be obviously one number that's smaller, well, a positive number that's non-zero that's our smallest, and we can figure out what that is too. So two issues here. In math class, is there a biggest number? No. Okay. Is there a smallest positive number? Does such a thing exist in math class? Huh? Okay. You claim that in math class there is a smallest positive number. Would you please tell me what it is? Huh? That's not positive. Okay, 1 is the smallest positive number you can think of. 0.01. Okay, well, I see your 0.01, and I choose to divide it by 10 and give you 0.001. That's smaller. So in math class, if you claim that you have the smallest number, I can just come along and say, oh, no, I'll just divide it by 2, and that number is smaller, and it's still a number, right? So there is no smallest positive number in math class. What about it here? Yes, there is, because we have a fixed number of bits for the encoding. Similarly, there's no largest number in math class, but there is here. Okay, and let's figure out what that number would be. Well, what do you guys think? We're talking positive, so clearly the sign bit being 0. Okay. What do you think the biggest exponent that we could write down is? How about that? Okay, what does that look like? 111 is an exponent. It looks like 7. What does it really count as? Hmm? 4. Okay, why 4? Okay, what's 7 minus 3? 4. Okay, why did we do 7 minus 3? Okay, so why are we subtracting 3 here? What's our exponent bias? 3, okay? So if I write down the biggest number I can think of that I can encode with 3 bits, that's 111, 7, okay? So it looks like 7, but it really counts as 4, okay? What would be, if I wanted to get the most number for my buck, I'd also make my Mantissa all ones, probably, right? All right, so what does this number decode as? Well, it's 1 point this times 2 to the third, or fourth, excuse me. Okay, 1 point Mantissa times 2 to the exponent. All right, so what does the 4 do? Okay, so the exponent here, how many positions do I move my radix? 4 to the right, and that gets me what? 1, 1, 1, 1, 1. Point 0, right? Okay, what is that? Well, I have a 1, I have a 2, I have a 4, I have an 8, and I have a 16, and so this is 31. Okay, so that's the biggest number that we can encode. Does that make sense? Okay, now, here's where it gets funny. We can encode numbers from 0 to 31. Okay, how many things can we encode between 0 and 31? A total of 128 of them, and that's including 0 and 31. Okay, so I've got basically 128 numbers that I can encode between 0 and 31. Would it make sense to sort of uniformly distribute them evenly across 0 to 31? Right, so if I were to draw them out on like a big number line, they'd all be evenly spaced. Okay, there would be a certain degree of sense to that. It turns out that's not the way it works. Okay, so and if we think about it, that kind of makes sense. Let's imagine that we're dealing with feet and inches. Okay, if I ask you to make me a 1-foot post and you're off by an inch, am I going to be a little pissed? Probably. Okay. If I ask you to make me a 100-foot post and you're off by an inch, am I probably not going to be too irritated? No. Okay. So the degree of precision that you want or will tolerate kind of depends on how big or small the number is. Okay. And that's sort of true in the floating point system, that the numbers that we're able to encode are not evenly spaced. We can encode some things with more precision than others. Okay, and the cutting wood, you know, to lengths or whatever, it's a crude analogy, but it'll work. Okay, okay. So let's, on the flip side, figure out what's the smallest number that we can encode other than 0. Okay. All right. Well, sign bit 0. We're dealing with the positives. Okay. What's the smallest exponent you can think of to write down? How about all zeros? Okay. And what's the smallest mantissa you can write down? This is a trick question. Okay. Why is it this? Yes. Okay. And all zeros, literally everything being 0, is a special case. That's the encoding of 0. Okay. So the smallest I can do besides that is to put a 1, I have to put it somewhere, as far away from things as I possibly can. And so we've got this. Okay, so now let's decode it and see what this thing represents. Okay, so 1 point mantissa times 2 to the exponent. Okay, well, so let me highlight the exponent bits. What was our color? Green for exponent. And red for mantissa. Okay, what does the exponent look like? 0. What does that really count as? -3. Okay, because we have to subtract off our bias. Okay, and what does the -3 as an exponent do to our radix? Okay, so negative exponent, which way does it go? To the left. Okay, by 3 positions, and so I would have 0.001 this. Okay, do you guys agree? Yeah? And I'll put a leading 0 out front just for cleanliness. Okay? All right, so what is this number? Well, this is where it's going to get annoying. Do we have any halves? Do we have any quarters? Do we have an eighth? Okay, do we have a 16th? Do we have a 32nd? Do we have a 64th? Do we have a 128th? Yes, okay. Now, I don't know what the hell 1 over 128 is. So, what did we say? We have an eighth plus a 128th. Okay, and so this is that as a base 10 number, 0.1328125. Okay, so does that make sense? All right, that's the best we can do. Or that's the smallest we could get here with our 8-bit thing, other than 0. Okay, now, how many of you guys are bothered by the fact that I can encode 0.132, but I can't encode 3.132? Right, 0.132 is pretty close to the 0.141 blah, blah, blah of pi, right? So I can't encode 3.1328 blah, 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 but I can encode 0.1328 blah, blah, blah. Does that bother you guys? No? Okay, well, that's maybe not the reaction I was expecting. But why does it make sense, though, that we've got this, we can encode that precise of a number, but we can't encode 3 that? Okay, think again like to my fence post thing. Right? Now, the sort of technical answer is that if I wanted to encode 3 whatever, that changes my exponent, and sort of all of these bits that are far over there kind of just disappear because I have to spend bits to encode the 3 of 3.14 whatever, right? And we'll look at this actually as a way to sort of talk about arithmetic. I guess we'll do that Friday, is let's take this number. We also can encode the number 3, okay? And let's do the arithmetic and add them. And the result that we'll get is not what you'd expect, okay? Because what would you expect to get? How about 3 blah, 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 right? But we won't get that. And that's interesting, okay? All right, so, yes. Okay, so did anybody bother to check that assignment that I screwed up that you couldn't get into? And can you now get into it? Oh, and we're all very happy that we can get into it. Dr. McKinney's a dum-dum, okay? So I shifted around some things on Canvas to take into account this screw up because, it turns out that some people consider it unreasonable to make an assignment due and not the night before the professor actually makes it so that you can access the assignment, right? Turns out that's yeah, people don't like that. So my bad. But okay, and here's where I have to get on my soapbox. How many people emailed me or said anything about that being inaccessible to me? One person. Out of how many that are in this class? 25. Although, looking at today's crowd, you wouldn't know that, Mr. Snook. And, yeah, we're missing all kinds of people. So, anyway, if you guys notice screw-ups like that on Canvas, please just let me know. Don't just assume that somebody else has. Okay? All right? Go away.